Hello! Today we are going to explore a fascinating problem from a Harvard exam known as the Lucas sequence identity. Our objective is to prove that for any prime number p greater than 5, the Fibonacci number at index p minus the Legendre symbol of 5 mod p is divisible by p. Before we start, let's briefly review the Legendre symbol, denoted as a over p in parentheses. For a prime p, the symbol is 1 if a is a quadratic residue modulo p, -1 if it is a non-residue, and 0 if a is a multiple of p. Since p is greater than 5, the symbol 5 over p will be either 1 or -1. Let's call this value epsilon. So, our goal is to show that this specific Fibonacci number is congruent to 0 modulo p. To tackle this, we'll use Binet's formula, which gives us an explicit expression for the nth Fibonacci number. The formula states that f sub n equals the quantity 1 plus the square root of 5 to the power of n, minus the quantity 1 minus the square root of 5 to the power of n, all divided by 2 to the power of n, times the square root of 5. We can rearrange this to avoid fractions by multiplying both sides by the denominator. This gives us a form we can work with using modular arithmetic. Now, let's substitute n equals p into the terms from Binet's formula. We need to expand the quantity 1 plus the square root of 5 to the power of p. To do this, we use the binomial theorem. When we expand this out, the coefficients of the middle terms are all combinations of p choose k. Here's a crucial property. Because p is a prime number, all the binomial coefficients for k strictly between 0 and p are multiples of p. This means that when we work modulo p, all those middle terms simply vanish, leaving us with just the first and last terms, 1 to the power of p plus the square root of 5 to the power of p. Since p is an odd prime, we can rewrite the square root of 5 to the p as 5 to the power of p minus 1 over 2 times the square root of 5. Now, we apply Euler's criterion. This states that 5 to the power of p minus 1 over 2 is congruent to the Legendre symbol 5 over p, which we called epsilon. Substituting this back, we find that the quantity 1 plus the square root of 5 to the power of p is congruent to 1 plus epsilon times the square root of 5 modulo p. By the exact same logic, the conjugate expression 1 minus the square root of 5 to the power of p is congruent to 1 minus epsilon times the square root of 5 modulo p. Take a moment to think about how cleanly the prime modulus simplifies these massive expansions. Now let's use what we just found to evaluate the Fibonacci number at the index p minus epsilon. Remember Binet's formula. We need to look at the difference between the two terms raised to the power of p minus epsilon. Let's analyze the first term. We can rewrite 1 plus the square root of 5 to the power of p minus epsilon as the pth power times the negative epsilon power. Substituting our result from the previous scene, this is congruent to 1 plus epsilon times the square root of 5, all multiplied by 1 plus the square root of 5 to the negative epsilon. Let's look at the two possible cases for epsilon. If epsilon equals 1, this expression simplifies to 1 plus the square root of 5 times its inverse. This simply equals 1. If epsilon equals -1, the expression becomes 1 minus the square root of 5 times 1 plus the square root of 5. This is a difference of squares, giving us 1 minus 5, which equals -4. Now, what about the second term in Binet's formula, the conjugate? If we follow the exact same steps, when epsilon is 1, we get 1 minus the square root of 5 times its inverse, which is also 1. And when epsilon is -1, we get 1 plus the square root of 5 times 1 minus the square root of 5. This again gives us -4. This is the magical step. Whether epsilon is 1 or -1, both terms in the numerator of Binet's formula evaluate to the exact same value modulo p. Because they are the same, their difference is exactly 0 modulo p. Going back to Binet's formula, this means that a constant times our Fibonacci number is congruent to 0 modulo p. Since p is a prime strictly greater than 5, it doesn't divide 2 or 5. Therefore, p must perfectly divide the Fibonacci number f sub p minus epsilon. And with that, we have successfully proven the Lucas sequence identity. We showed that the Fibonacci number at index p minus the Legendre symbol of 5 mod p is a multiple of p. Thank you for watching.